All right, we are at section 17.2, standing waves. Let's share the PowerPoint. Um, and here we have two speakers, same with the same audio signal, uh, with the wave facing each other. And so we're going to see what happens when this occurs. You have y equals a sine kx minus omega t, and y2 is equal to a sine kx plus omega t, because they're going in opposite directions. Um, the kx is just the position. You remember k is called the wave number. It's 2 pi over the wavelength. So if we add these together, y1 plus y2, we get a sine kx minus omega t plus a sine kx plus omega t. One is minus omega t, the other is plus omega t. And we're going to use uh, a identity sine of a plus b is equal to sine a cosine b plus cosine a sine b, or sine a minus b is equal to sine a cosine b minus cosine a sine b. And if we use that and substitute, we'll get that y is equal to 2a sine kx cosine omega t. And when we look at this, it produces a standing wave. The amplitude of the vertical oscillation of any element of the string depends on the horizontal position of the element. Each element vibrates within the confines of the envelope function 2a sine kx. So the 2a sine kx is the envelope of this standing wave. The nodes occur at kx, where kx equals 0. So at pi, I'm sorry, the nodes occur at kx equals 0, pi, 2 pi, 3 pi, 4 pi, and so on. And it was every 180 degrees, every half wave, they occur. X is equal to 0, pi over 2, pi, 3, I'm sorry, I'm saying pi, it's lambda. X equals 0, lambda over 2, lambda, 3 lambda over 2. So in general, that's n lambda over 2, where n is equal to 0, 1, 2, and so on. So at every half wavelength, um, 0, 1, 2, it's every half wavelength you get these nodes. Okay, and the antinodes, the peaks, are at kx equals pi over 2, 3 pi over 2, 5 pi over 2. So these are like, the first one is like 90 degrees. So x is equal to lambda over 4, 3 lambda over 4, 5 lambda over 4. So the n is equal to x is equal to n lambda over 4, where n is equal to 1, 3, 5, the odds. Okay, and the distance between adjacent antinodes is equal to lambda over 2. The distance between adjacent nodes is equal to lambda over 2. And the distance between a node and an adjacent antinode is lambda over 4. Okay, so wave pattern. So you notice y1 and y2 are both in phase. And so the antinodes and the nodes occur at the same place as the original equation. Now, notice that y1 and y2 are opposite each other. So they cancel each other. That's the destructive interference. And then at the back, that's 1/4 of a period. A half a period, they're back in phase. They're they're 180. In other words, we started off with both of them going up. Now they're both going down as these waves travel in the velocities indicated. Okay, let's go to a little quick quiz. Consider the waves in the figure to be waves on a stretched string. Define the velocity of elements of the string as positive. They are moving upward in the figure. At the moment the string has the shape shown by the red brown curve, what is the instantaneous velocity of elements along the string? Is it 0 for all elements, positive for all elements, or negative for all elements, or it varies with position? And the answer is 0 for all elements. The pattern shown in the bottom figure corresponds to the extreme position of the string. All elements of the string have momentarily come to rest. Okay, at the moment the string has the shape shown, the instantaneous velocity of the elements along the string, it's 0 for all elements. Okay, here's another one. Consider the waves in the figure to be waves on a stretched string. At the moment the string has the shape shown by the red-brown curve, what is the instantaneous velocity of the elements along the string? 0 for all elements, positive for all elements, negative for all elements, or varies with the position of the element. And in this case, it varies with the position of the element. Near a nodal point, elements on one side of the point are moving upward at this instant, and elements on the other side are moving downward. So it varies with the position of the elements. Okay, next we'll do boundary effects.